This is section 16.2, double integrals over general regions. In 16.1, we did double integrals where the base region was a rectangle. And we realized that when the base of your integral is a rectangle, the x bounds and the y bounds are both numbers, and everything is kind of easy. If you want to do the integral in a different order, you just switch where the numbers are. When the base is not a rectangle, it's a little bit more complicated, and we'll figure out how to deal with that this time. So here's our objectives. We're going to be doing these iterated integrals. These are double integrals. Figure out what they have to do with area, and figure out how to turn area back into double integrals. Then we'll have this new terminology, simple. A simple region can be either vertically, you can have a vertically simple region or a horizontally simple region, and we want to nail down what that means. Then figure out, in general, how to switch the order of integration when you have an integral. We saw last time that it's really important to be able to do that to change a problem that needs 2 integration by parts into a problem that needs 1 integration by parts. So yeah, then finally we'll use this trick to find some volumes. So let's jump into this. First, let's find this integral. What we decided last time was that you can think of this as there's an inner integral and an outer integral. You can put off the outer integral until later, and then do the inner integral. And this inner integral is an x integral, so I can factor out anything I want to that doesn't have any x's in it. Here, y does not depend on x, so I can factor out y. Technically, I could have taken the 2 out also, but I was happy to keep the 2 because the integral of 2x dx is x squared. Now the key here is this y is not part of our inner integral anymore. It's just chilling here. And the integral of 2x dx is x squared. Now the bounds, the x bounds, are from x equals 0 to x equals y. If you write that, then it's clear what to do. You should plug in y for all the x's, so plug in y for this x. And I'll have y times y squared. Well, that's y cubed. Finally, this is just a regular old Calc 1 integral, so it's a fourth y to the fourth from 0 to 1, and that's a fourth. So this integral came out to a fourth exactly. Now, when the bounds of both integrals are numbers, like if it was 0 to 1 and 0 to 2, that would mean that we were integrating over a region that was a rectangle. But this time, the upper bound for the x is not a number. It depends on the y, so it's not a rectangle anymore. So what does this look like? Well, let's try to get a picture of it. That's what this draw a sketch of the integration region means. The y values go from 0 to 1. And the key thing here is that it's not like this is 1 and this is 0. This is y equals 0 and y equals 1. And that's important because it can get tricky, especially as we get into triple integrals later in the class. Like, what is 2? What does 2 even look like? And sometimes 2 will be like a circle or a cone or something weird. So if you can keep track that this one is actually y equals 1, oh yeah, this is a horizontal line at y equals 1. Then the x bounds are from x equals 0, okay, that's this line, to x equals y. Well, x equals y is this line. So the lower bound is y equals 0, the upper bound is y equals 1, the left bound is x equals 0, and the right bound is x equals y. So what's the region? Well, for any value of y between 0 and 1, we go from x equals 0 up to x equals y. So for any y, we go from x equals 0 to x equals y. For any y, say this y, we go from x equals 0 up to x equals y, all the way up to here. So the region is this triangle. This is the main insight that you need to get from this section, is that when you see bounds like this, the bounds are a rectangle if the bounds are all numbers. If the bounds are not all numbers, then it's some other shape, but that there is a shape in the xy plane that the bounds correspond to. Okay. So let's try to like put stuff together so that we can get up to exchanging the order of integrals. That's what we wanted. That's our main like algebra technique that we want to be able to get to. So first, what does this mean geometrically? So if a is less than b, what do we get here? Well, if a is less than b, this just comes out to b minus a, this integral. So it's the length of the interval. Let's get a different color here. This integral, when there's no function in here, it's just the length of the interval. What's going on here? Well, now this is the integral with some bounds of dx dy, and this is dA, which is a little bit of area. So this is the sum of all the little bits of the area. So in total, this is the area of a rectangle. In both cases, the reason I've changed the color like this, in both cases, when you take an integral and there's no function in there, it's just the integral of dx or the integral of dA, what you're finding is the size of the base of the integral. This integral is based over an interval. So this integral comes out to the size of that interval. This integral is based over a rectangle. And so this integral comes out to the area of that rectangle. It doesn't always have to be a rectangle, though. So let me get my blue back. So we've got a problem here that's asking us to find the area. This is a problem that you did maybe at the end of Calc 1. Definitely you did at the beginning of Calc 2. It gives you two curves, like y equals 1/2 x and y equals x squared plus 1. I don't think these intersect. No, I'm not sure. Do these ever intersect? I don't like this equation, so I'm going to multiply it all by 2. Now I'm just curious if this even has any real solutions. If it had real solutions, they would look like this. B squared minus 4 times 2 times 2. Okay, so these don't intersect, so it really does look like this. Up here we've got the point 4, 17, and here's the point 4, 2. And the question's asking what's the area between these from x equals 0 to x equals 4. Now when you did this in a Calc 1 or a Calc 2 class, what you would do is you would say, okay, well the area, I have a bunch of different formulas for the area. One of them is the top function minus the bottom function times dx. So this is before Calc 3. You were able to solve this problem. The top function was x squared plus 1. The bottom function is 1/2 x. I can multiply that by dx and take the integral from 0 to 4. And we'll get an answer. From 0 to 4, plug in 4, we'll get 64 thirds plus 4 minus 4. Weird. So we get 64 thirds. So this is the Calc 1 or Calc 2 way of finding this area. Now, in Calc 3, what we realize is that this dA, it doesn't need to be broken up into like a function and a differential. Instead, you can just make the whole region be encoded in the bounds of the integral. So instead of the bounds just being the x's and like the height of the region being in the function, instead you can say, whatever, I'm just going to put dA here, and I'll get the whole region encoded in here, in the bounds. X goes from 0 to 4, and y, oh wait, since I've decided what order, x goes from 0 to 4, and y, at the low end of y is half x, and the high end of y is x squared plus 1. So the Calc 3 summary of how to find the area is that the area is the double integral of a little bit of area. This perspective is just get everything about a region in the xy plane, just get it all in the bounds, and then there's no function here to deal with. The answer will come out the same, because when you do this interior integral, you get, well, the exterior integral is going to be the same. The one on the inside, the integral of dy is y, and you plug in the two bounds, and you get x squared plus 1 minus 1/2 x, which is exactly what we had before. So you'll get the same answer, it's just, it's possible with double and triple integrals to get a whole bunch of the geometric information out of the integrand and up into the bounds, and that will end up making a lot more types of problems possible. Here, yeah, this is a good note that if, just like in Calc 1 or Calc 2, if sometimes x squared plus 1 was below 1/2 x and sometimes it was above, you would have to split the integral into different pieces. But essentially the point here is we get some x bounds, we get some y bounds, and the y bounds can be functions of x. One more note is that the outermost bounds are always numbers. If you've got bounds on the inside, the variables in there, they have to go away somehow. Like any variable in a bound has to get integrated away eventually. So if there's a variable in the bounds, it has to be like getting ready to get integrated later. These x's that are in the inside integral's bounds, they'll get integrated away when we do the outer integral. So the outermost bounds are always numbers. Okay, let's try to do this with these weird functions. So we'll just set up an integral, a double integral, that finds the area between these graphs. So here's y equals 3x. We're going from y equals 0 to y equals 2. So this is at y equals 2. X is, if y is 2, then x is 2/3. But it does go through the point 0, 0. Then we've got y equals the square root of x minus 4. Uh-oh. So square root of x minus 4 is all the way over here. And goes this way. This equals 2. Where does this equal to? Square both sides. Looks like we get y equals 2 at x equals 8. So we're trying to find the area between y equals 3x and y equals square root of x minus 4, between y equals 0 and y equals 2. So it's this area. Now, notice that we've got this issue where the bottom function changes as we go throughout the region. So here the bottom is y equals 0, but then as I keep going, the bottom function is y equals square root of x minus 4. Similarly, the top function over here is a line, and the top function is a different line. So I don't want to orient my integral that way. Instead, I want there to be like the left function is always the same and the right function is always the same. When that happens, it's best to say, okay, my outer integral is going to be the y's. Y goes from 0 to 2. And then the inner integral can be the x's. This region, it starts at, like for any given y, it starts here and goes over to here. So what is that? Well, here's a wrong answer. It's not this. It can't be this because, first of all, like these are x bounds. So this is supposed to be a value of x, and this is supposed to be a value of x. But what I've put in here are values of y. Like this is y equals 0 up to y equals 2, and this is y equals 3x up to y equals square root of x minus 4. So I know that can't be right. The other issue is that after I finish this inner integral, if I have x's here, then I'm going to just still have x's, and the integral dy on the outside won't get rid of them, so the final answer won't be a number. So I know these bounds can't be correct. I need to put x bounds in here, so that means I need to find what x equals. So let's solve these for x. If y is 3x, then x is 1/3 y. That's the left side, that's the low end of the x's. If y is square root of x minus 4, I can square both sides. And x is y squared plus 4. This is the same work you did in Calc 2 when you were setting up the integral, but it's under a different perspective where we say, well, all this geometric info about the shape, about the region, that should all be in the bounds. So this is my setup, is that the area is the double integral of dA over my region. And then my region R is encoded in the bounds. When I do the inner integral, the answer is going to have some y's in it, but that's okay because the outer integral will do the integral with respect to y, so I'll have all numbers at the end. So this lets me do this. So let's just do it. So I'll do the inner integral first. After you finish the inner integral, you'll have the setup that you would have used in Calc 2. And then you can do this integral. From 0 to 2. Plug in the 2, you get 8/3 plus 8 minus 4/6. 4/6 is 2/3. Let's get everything in terms of thirds. So I have 8/3 plus 24/3 is 32/3, minus 2/3, that's 30/3. So my answer is 10. So the area of this region is 10. I don't know any way to find this area without some kind of integral. If you remember how Calc 2 worked, you can find the area by starting at this step, but it will be more valuable to complete this class if you realize that the whole region, any region in the plane, should be encoded all in the bounds of the integral. Okay, what's going on here? This says, how does the following calculation check our answer? Explain the geometry of this expression. So what's going on here is that because we were finding an area, you could certainly find the area lots of different ways. We found the area directly. We found the bottom and the top and the left and the right and put it all in the bounds. This plan, and you can always try other plans to check your answer, was to say, well, here's 16. 16 is 8 by 2, which is this box. So here's 16. This whole box. The region I care about is in that box. The region I care about is this region. But I don't want, the 16 has some extra stuff. So to make the 16 correct, I'm going to have to remove this triangle. But this triangle has an easy to find area. Its height is 2 and its width is 2/3. So the area of this triangle is half times 2 times 2/3. That's this. So we say start with 16, which is the big box, take away the triangle, and then the other region that we need to take away, oops, I already used red. The other region we need to take away is this region, and this region can be found by integrating square root of x minus 4. So that's this. So if you wanted to check your answer, whenever there's a geometry question, you should feel like there's at least 30 ways to find the area of any given region, like to answer any geometry problem. And so if you have time to check your answer, you should check your answer like that. Okay, let's get the vocabulary word for what happened here. The region that we had there, it had the same function was on the left boundary of the area, and the same function was on the right bound of the region for the whole region. In that case, it's like, I want to say that the region is simple in that direction. Where, let me see if I can find the other. Did the first page have one that was simple in the other direction? That's simple in both directions. This one, the left boundary and the right boundary change depending on where you're looking. Like if you're at this height, the left boundary is the parabola and the right boundary is a line. Wherever if you're down here, the left boundary is this other line and the right boundary is this other fourth line. So it's not simple in this direction, but it was simple in the other direction. The bottom and the top functions are always the same. So those two options are called horizontally simple and vertically simple. So if you've got a region and the bottom function and the top function are fixed, so like this, G1 and G2. You've got some like x bounds that are numbers and some y bounds that are functions, and the bottom function and the top function are where it's at. Then the region is called vertically simple. If you don't have that, but, well, if you don't necessarily have that, but you have a fixed left and right boundary, then that's called horizontally simple. So this would be like, you've got some weird stuff going on the right and the left. And thinking of it as having a right boundary and a left boundary is more productive. So this would be like h1 of y and h2 of y. Here the y bounds will be numbers and the x bounds will be these functions. In the two cases, you will use the different order of integrals to set up the integral. Okay, so let's find an area. Let's do it a bunch of different ways. We'll do it a way that that we have been able to do since Calc 1, and then we'll do it vertically simple and horizontally simple. This kind of exercise is something you already did in Calc 2, but we're trying to really focus in on how much information we can move into the bounds of our integrals. We need as much stuff in the bounds as possible. You'll see why later. This is not convincing, but it's actually really worth it. That's why there's a whole section for this. Okay, so we're looking at y equals x squared, the x-axis, and x equals 3. So we're looking at this region. In Calc 1, we would have said, oh, this is what an integral is for. It finds this area. Now you know, after seeing like all of Calc 2 and a whole bunch of Calc 3, that integrals are used for lots and lots of things, not just finding areas under functions. But this was just where it was at in Calc 1. So the area is 9. Now, if we think about this as being a vertically simple shape, we can get all the info out of the integrand and into the bounds of an integral. Now, which kind is vertically simple? Vertically simple is saying, well, think about there being a bottom function and a top function. So the vertically simple perspective is to say, okay, nice region. It has a bottom function here and a top function here. In that situation, the area is, well, the bottom function and the top function are y equals something, possibly functions of x. So those have to be on the inner integral. This is your, these are y bounds, so this is the y integral. Then the outer integral will be the numbers. In this case, it's the x's, so this goes from 0 to 3. This seems like a useless exercise, but I promise it's worth it to get. You really want to be integrating 1 whenever possible. So actually doing this integral, you end up immediately turning it into the previous integral. It's not that big of a surprise. The integral of dy is y. You plug in 0 and x squared for y, and you get the integral of x squared dx, which we just did. It's 9. So this is the vertically simple perspective. This region is vertically simple. The whole region has the same function on the bottom the whole time and the same function on the top the whole time. The horizontally simple perspective is, well, instead, you should think of there being a left boundary and a right boundary. So here's the left side, and here's the right side. The left side is, okay, we were given it as y equals x squared, but we're going to think of it as x equals the square root of y. And the right boundary is x equals 3. What's this point up here? It's like 3, 9. So from this perspective, our area is going to be still an integral, but now the like inner integral goes from the left side is square root of y, and the right side is 3. And those are x bounds. This is x equals square root of y up to x equals 3. And then the y bounds are on the outside. These will be what's the lowest y and the highest y. That's from 0 to 9. Notice that the integrals look extremely different, but they're calculating the exact same thing. Being able to switch between them is the goal of this section. So we're really trying to like focus in on how to get the info into the bounds. If you do this integral, you'll get the integral from 0 to 9 of, okay, you'll get x from root y to 3. So you get the integral from 0 to 9 of 3 minus square root of y dy, which is 3y minus, okay, I have the 1/2 power, so I'll make the power 1 bigger, that's 3/2, and divide by the new power. So 2/3 y to the 3/2 from 0 to 9. Okay, plug in 9, the zeros won't matter again, so plug in 9, I get 27, minus 2/3 times 9 to the 3/2. 9 to the 3/2 is 1.5 copies of 9. So like 9 and also the square root of 9. Here's 9 to the 3/2 power. Is 9 times 3. Anyway, I get 27 minus 18, that's 9. So I get the same answer both ways. One of these integrals is a lot easier than the other. And this happens often, where one of the two ways is better than the other. It happened in the last section, it's going to happen all the time. So if someone hands you an integral and you don't want to do it, the main Calc 3 way to get out of doing a like double or triple integral is to switch around the order. So if you're given this question, you would say, no thanks, I'll do this question instead. And we'll get there shortly. Okay, let's do this one. We're trying to find the area between the x-axis. I don't know where these are. So the x-axis, this is y equals 0. 5x plus 3y equals 15. In this form, you get the intercepts very easily. So like if you imagine x equals 0, then you can see that y equals 5. So if x is 0, then y is 5. And if you plug in y equals 0, you can see that x is 3. So this is going to be a line through these 2 points. This one, the vertex is at, it's a parabola that's open down, but the vertex is at x equals minus b over 2a, which is 2. So the vertex of this parabola is going to be at 2, and then plug in 2. Minus 4, plus 8 is 4, plus 5 is 9. Okay, let's get a picture. Looks like it's all mostly happening in the first quadrant. Oh, it says first quadrant. Should have paid attention. So the x-axis, that's this x-axis here. I've got 0, 5. 2, 4, 5, and 3, 0. Let's stretch out the scale a little bit. Three, 0. So here's the line in the question. That's 5x plus 3y equals 15. Then I've got this thing, this parabola, which starts up here at 2, 9. The y-intercept is at 5. So it looks like this. And then it's going to be at 5 again over here. Yikes, I don't know where this actually crosses. Gross. Let's see. I don't like this negative x squared, so I'll multiply through by minus 1. Then, I don't know if you're into this, but I don't really like the quadratic formula that much. I prefer to complete the square. X squared minus 4x to make it a perfect square would get a plus 4. But I can't just change minus 5 into plus 4. That's off by 9. So I have x minus 2 squared equals 9. So that's x minus 2 is plus or minus 3. So x is 2 plus 3 or 2 minus 3. So here's x equals 2 plus 3. That must be at 5, 0. So the region we're looking at is this one, in here. The problem here is that the region's not simple. It's not vertically simple because, let's outline it. The bottom of the region is here for part of it, and the bottom of the region is this line for another part. So it's not vertically simple. It's also not horizontally simple because the left side of the region is here for a little while, and the left side of the region is over here for a little while. So it's not simple in either direction. Nice tracing. So there's no way out of doing this integral by splitting it up into two pieces. So let's split it up into two pieces. I don't know. What's easier here? What I'm doing is I'm looking for a way to I'm looking for a way to think about this geometrically so that I don't have to do two difficult integrals. Like I'm hoping to see it as like an integral of a complicated region plus a rectangle, or an integral of a complicated region minus a triangle. This one it looks like I can get away with. I can do this bigger region, which is actually simple in one of the directions. I can find the area of this region and then subtract this triangle. The triangle is 3 by 5, so its area is 3 times 5 divided by 2. So this is, I'll just write 15 over 2. So if I can do this bigger region that's outlined in green, which is simple, it has a top function and a bottom function, then I can just subtract 15 over 2 and I'll be done. So the big region is, I'm thinking of it having a top function and a bottom function. The top function is this y equals x squared minus x squared plus 4x plus 5. And the bottom function is y equals 0. Because those bounds are y's, that means this inner integral is a y integral. And then the outer integral will be an x integral, and it's from 0 to 5. So I need to do this integral, and then in total, the total area will be this integral minus 15 halves, because that minus 15 halves is this triangle that I'm going to take out. I'm sure there are like 13 other ways to do this. Like you could have cut the region here and done these two pieces, or you could have like cut the region here and done these two pieces. You can do pretty much anything you want, but I found a bigger area that I could take away a triangle to get the answer, so I'll do it that way. Anyway, we'll do the y integral first. The y integral is really simple. And then this is going to be like a really long section, so I'm just going to skip doing this, even though that's kind of bad practice. The final answer in the end comes out to 155/6. But we have a lot to think about as far as like switching bounds and stuff, and I'm out of paper anyway, and so we're just going to move on. But the point is, when you want to find an area, you should be looking for simple regions that are either vertically simple or horizontally simple, so that you can do the integral like all at once. If it's not vertically or horizontally simple, you have to like expand your thinking and find a simple region so you can integrate it. Okay. So what are we doing? We did this a couple pages ago, but a single integral with nothing inside, that's the length of the interval. It's the length of the interval from 1 to 5. I don't know what I wanted to write in this space. Or I guess if you were back in Calc 1, you would think, oh, integrals are always area. So you could think of it as it's the area of the region above that interval that's below y equals 1. Like you would say, oh, this is the integral of 1. So you can either say, oh, yeah, that's the length of this interval. Or you could say, well, back in Calc 1, I would have thought of it as I've got an interval from 1 to 5, and there's a function y equals 1 hiding in here, and I'm finding the area of this box. Okay, similarly, this integral, you can think of it as meaning, okay, well, whatever, if you're just taking an integral and there's no function in here, you're just integrating dA. So you're finding the area of the region that's described by this rectangle, by these numbers. This region is x goes from 1 to 5, and y goes from 2 to 3. It's a rectangle. But you can always instead say, well, what if you actually give meaning to this 1 that's hiding in here? That 1 could be a height. So we could say this integral from 1 to 5 and 2 to 3, that's just telling you the base of a 3D object, and the function is telling you how tall it is. So this is the volume of a solid that's like sitting above that rectangle, and it has height 1. So now we're like, okay, here's x and y. X goes from 1 to 5. Y goes from 2 to 3. And I've got this box back down here. But then I'm integrating 1 dA, and you can think of 1 as being the height of the box. So the same integral can be thought of in multiple different dimensions, depending on whether you're thinking of this 1 as having a real meaning, like the function that you're integrating. Okay. So what if you actually put a function in there that's not 1? If you put a function in there that's not 1, now you're stuck. The only way to think about this is to go up a dimension. That this is the volume above the region that's defined by the limits, and under the surface that's the function. So when you see a double integral of a function, that's the volume under the surface. So like z equals f of xy is some crazy surface. And then the bounds 1 to 5 and 2 to 3 are, you like look under it, and you make the box, the rectangle, that goes from 1 to 5 and 2 to 3. And combined together, those make a solid. I don't know if you can see that, what I'm trying to get at here. But it's a solid under a surface above a rectangle. That's what a double integral can mean. I'm skipping that for now. I don't want a 2-hour video. Okay. So we're thinking of a double integral over a region of a function. And the integral might be, it's going to be dA. And dA can be written either dx dy or dy dx. When we see this, when we see a double integral of a function over a region, we're thinking of it as like the filled in volume. I don't know, maybe like the filling out of a 3D volume that's above a 2D region with different heights. I don't know what we're supposed to put in this box. So it's just like in Calc 1, when you had the integral of a function, you thought of it as the area under the curve. Now it's, when you have the double integral of a function, it's the volume under a surface. So let's find a volume. So we're going to go between the coordinate planes. The coordinate planes are x equals 0, y equals 0, and z equals 0. And then also this plane, 6x plus 2y plus 4z equals 12. We're trying to find the volume of the solid that's under this plane and like bounded by all the coordinate planes. This form of a plane makes it easy to see the intercepts the same way that I did the intercepts before. So let's try to get a picture here. So if you let x and y both be 0, you can see that z is 3. If you let x and z be 0, you can see that y is 6. Oh no, I forgot to undo. Ah. If x and z are 0, y is 6, yeah. And if y and z are 0, you can see that x is 2. So the plane, 6x plus 2y plus 4z equals 12, cuts out this region in the first octant. It cuts out a pyramid. Okay, if someone asks me to find the volume of a pyramid, I'm using the geometry formula. It's a third base times height, which here the base is a triangle that's 2 by 6, and the height is 3. So if you give me a bunch of different options of how to find the volume of a pyramid, I'm going to use the formula, like the geometry formula. But the point here is that we can also do it by integrals. So how will we do that? Well, we're going to say that the volume is the integral, the double integral, of a function. Not that kind of function, this kind of function. 2 inputs, dA. This says use both orders of integration. So let's just pick one. The function is going to be, well, let's solve for z. Z is 12 minus 6x minus 2y, all divided by 4. So z is going to be 3 minus 3/2 x minus 1/2 y. That's z. This will work for either order, but let's pick an order. Let's say that we are thinking of What's the right way to say this? I guess you can just pick an order. Let's say that we try dx dy. We'll do the other one next. The key thing here about how to get the bounds is that the bounds represent the region that you're integrating over. That was the whole point of all this stuff where I kept moving stuff into the bounds. It was like you can get an entire two-dimensional region encoded in the bounds of a double integral. So when I'm going to make the bounds don't have to do with the whole picture. The bounds come from just the part in the base, which here is the xy plane. So what I recommend you do when you're building the bounds for a double integral over x and y is you redraw the picture in the xy plane, just the part in the xy plane. It's going to go over to 2, 0 and up to 0, 6. In the xy plane, this triangle is this triangle. And what's going on with this line? Well, this line is what happens on the plane. See, we're on the edge of the plane here, when z equals 0. So that's 6x plus 2y equals 12. This picture is how we'll get the bounds for our integral. So if y is on the outside, then the y's can't depend on anything. So you just tell me the lowest y and the highest y. That's 0 to 6. But then the x's, well, once you've picked a y, what's the lowest x and what's the highest x? The lowest x is this boundary, and the highest x will be on this boundary. So the lowest x will be x equals 0, and the highest x will be whatever this is when you've solved for x, because it's an x bound. So I need to put an x here. So solve this for x. You'll get 12 minus 2y, all divided by 6. So that's 2 minus a third y. So here's one setup. We picked an order, dx, dy. We noticed that because we're just about to build the bounds in terms of x and y, we should draw the xy plane. And then the outer bounds were 0 to 6, because it had to be numbers, and the inner bounds were the left function and the right function, which both had to be in terms of x. We had x equals 0 and x equals 12 minus 2y over 6. The other way to set it up would have been mostly exactly the same. But if we do it, oops, don't do the exact same thing. If we do it dy dx, now the x bounds are on the outside, so they have to be just numbers. That'll be from 0 to 2. And the y bounds are whatever is the bottom function and whatever is the top function in terms of y. Here's y equals 0. And here's y equals, well, I don't know, let's solve for y. That's 12 minus 6x all over 2. So of the three methods, using a geometry formula, using dx dy, or using dy dx, clearly the geometry formula will win every time. But among these two, if you had to pick one, which one would you pick? I recommend picking the one that has no fractions. So you just do this one. Let's do one of them and make sure that they come out to 6. So I'll do the inner integral first. The outer integral is going to sit here waiting for us. The inner integral is an integral with respect to y. So I'll get 3y minus 3 halves xy minus a quarter y squared. The bounds here, the y bounds, are from y equals 0 to y equals 6 minus 3x. So then I need to plug these in for y. So I'm going to have 3 times 6 minus 3x minus 3 halves x times 6 minus 3x minus 1/4 of 6 minus 3x squared. Oh no. Okay, let's go. Answer's supposed to be 6 at the end, at least we know that. So I'll distribute everything. I'm hoping for a lot of cancellation. 3 halves x times 3x is 9 halves x squared. That's not good. And then when we square this, 2 times 6 times 3 is 36. So let's collect all the like terms. The constants, I've got an 18 and a minus 9, so that's 9. The x's, I've got minus 9, minus 18, plus 9, so that's minus 9. And then the x squareds, I've got 9 halves, minus 9/4. That's minus 9/4. Do this x integral. It's easy to get lost in the weeds here. Remember that the main thing you should be watching out for is after you finish the y integral, all the y's should be gone. And they were. Plug in 2, we get 9 times 2, minus 9 times 4 over 2. No, it's not right, is it? Minus 3/4 times 8. So I've got minus 6. I know the volume of the pyramid isn't minus 6. Okay, but we knew the answer was 6, so this should be easy to fix. Let's try to find the error. This minus is my suspect minus. If I could just change this into plus, it would be correct. It's got to be minus there. It's this minus and this plus, but these look good. Okay, what did I do? I guess we'll cut here for me to find the answer, for me to find what I did wrong. And cut. Okay, found the error. The error was I had plus 9 halves minus 9/4. Plus 9 halves minus 9/4 is in fact plus 9/4. So we got 6. I know that's not a rousing review of double integrals, but I think you're getting the point here that the whole goal is to try to get information about a region to be encoded in the bounds of a double integral, instead of being in the integrand of the integral. Okay, let's do the last example. So this one gives us an ellipsoid, which is a surface. Z equals the square root, so it's always going to be positive z's. Then we're going to be between this ellipsoid and z equals 0. That's the xy plane. So I already have a base idea of what's going on. I've got x, maybe just the positive thing here. It's not the right way to go. So I've got the xy plane, and then above that is some kind of like spheroid thing. Like the top half of a those curves did not help. Let's make it a little bit taller. I don't know, the top half of a football or something. Giving it another bound of y equals 0 slices it again to slice off only the, to slice off so we're only got the part where y is positive. So now it's like a quarter of a football. Okay, how will we do that? Well, the perspective of this section is that we should go down to the xy plane and figure out what this region is in the xy plane. If we can figure out what the region is in the xy plane, then we can write that the volume is the double integral of our function dA, and all we'll need to do is figure out the region in the xy plane, we'll call it R, figure out those bounds. If we figure out good bounds for that, then it's all set up and ready to go. So let's do that. We'll go down and look at just the xy plane. In the xy plane, this surface has z equals 0. So in the xy plane, we're interested in 0 equals this square root. If I simplify this a little bit, I'll be able to draw a picture of it. I already know that I'm only going to have positive y's. That's why I'm only looking in this positive part, where y is positive. So I'll square both sides and add the x squareds and the y squareds over to the other side, and I get x squared plus y squared over 9 equals 1. This is an ellipse. It's an ellipse where if x is 0, you can see that y would be 3. And if y is 0, you can see that x would be 1. So y is 0, x is 1. Ooh. Or y is 0, x is minus 1. And if x is 0, then y is 3 or minus 3. So we'll be up here at 0, 3, 1, 0, and minus 1, 0. So here's our ellipse. That ellipse there is this curvy part, and this flat part is this flat part. This region is the region R. Now we ask ourselves, do we want to think about it as being horizontally simple or vertically simple? Which is the question, do you want to think about it as having a top function and a bottom function, or a right function and a left function? And here it will be easier if we think of this being a top function, because then the bottom function will be y equals 0. And this y equals 0 is critical because it tells me that my inside integral is going to be the y integral, because I have a bottom function and a top function. So I can set that up now. I'm going to have the inside integral is going to be the y integral, and the outside integral will be the x integral. All this other stuff is going to be the same. So the inside integral, it has bounds where the bottom function is y equals 0. The top function is whatever this is, so let's figure it out. Solve for y. Subtract x squared, multiply by 9. Take the square root. That comes just from this, solving for y. Then the outer integral is an x integral, so you need to give it the x bounds. And the outer integral is just the scalars, just the numbers. So this is minus 1 to 1. So this is our integral, set up as a double integral with the region R being converted into these bounds. Okay, so now we need to actually do this integral. This is looking like it's kind of a mess. In fact, I don't really want to do this integral right now, because to do it, I would have to do a trig substitution. So you should note, probably needs a trig substitution in either order. Anytime you have an integral that seems like it needs a complicated method of computing that integral, even if you liked doing integrals in Calc 2, your mindset should be to try to escape them when possible. In fact, this one we will be able to escape. And the way that we'll escape it is the next section. So that's why this question just said set up. In the next section, we'll find that if everything is made of like circles and ellipses and stuff, we're really using the wrong coordinates here, dy and dx, and we should use better coordinates. You'll see in the next section. But let's just quickly recap what the main idea was here. So back at the very beginning, like what were the objectives? The objectives were, we were trying to figure out how area was related to double integrals, these iterated integrals. And the point is that, like, if you get all the info of a region up into the bounds of the integral, then you've done it, and your integral finds area. Once we get down into these, the key idea is that if you care about the order, like if you care about dx dy or dy dx, the difference between those is between thinking of left function and right function. That would be that the inside integral goes from x equals something to x equals something else. So having a left function and a right function would be dx dy. Or if you want to think of there being a bottom function and a top function, here the bottom function would be this, and the top function would be this, and those would be y equals various things. In that case, the inner integral is a dy integral. Every double integral can be done either way, and sometimes one way is easier than the other. But the main idea is that to switch the order of the integral, you have to go draw the xy plane, draw the region in the xy plane, and then figure out what the bounds are just in the xy plane. So do some homework, practice it, and you'll be good. That's 16.2.